We've been using GeoGebra to work with this statistical testing. Uh, there's a lot of different. You can look online. You know how we added in that data analysis package. There are other add-ins or add-ons that you can find that you can download into Excel. There are, if you're a person that likes to use Google Sheets, obviously Google Sheets is the Google version of Excel, two different companies, but a lot of the commands and things that you can do in Excel, you can do in Google Sheets. The thing in Google Sheets is that you can find add-ons that will run some of these tests for you. What I've been realizing, though, some of those add-ons are kind of buggy, just because they're not made. Obviously, they're not made by Google; they're made by a third party. But when we use Excel, the way that the data analysis tab here works, this package works, is that we have to have the raw data established in columns, right? Okay. We cannot use the process data. So what I mean by that is this information here. Okay. We don't have the raw data. We already have I think I think the add-on that I saw in Google Sheets called this a summary of the data. Okay. Which I think is a good way of summarizing what this is. You can't type that into Excel and get it to do the test that we want it to. Okay. So Excel kind of has a fault there. But we can do that if we use GeoGebra. Okay. So I know it's two programs to get the job done, but it's better than doing it maybe by hand. Okay. So if you have GeoGebra, now you'd have to download this. GeoGebra has a web-based calculator, but for whatever reason, they do not incorporate their probability calculator on that web-based calculator. So if you want this, and I know not many of us have GeoGebra downloaded on our computers, if you go to geogebra.org, okay, and you can see here, basically, if I start calculator, it's going to give you an option. You can do these four things, okay, which obviously work for probability, and it's not there. So that's why you got to download it. Maybe in the future they'll add it back in. But what you're going to want to go to when you get to GeoGebra is down here. Where is it at? Somewhere should say downloads. App downloads. Click on that. And I don't like the interface of GeoGebra Classic 6. I like Classic 5. Just the one that I learned with, so it makes visually and finding the objects that I want. I like the 5. Okay. But if you download that, then when you open it, you can go up to your view, and you should have your probability calculator there. Okay. So what's nice about this is that when I click on statistics in the probability calculator, we have a drop down of all the different hypothesis testing that we've gone through so far, and some of the hypothesis testing that we will go through. Okay. So the first one where we're talking about here with this example, which is talking about the difference in means. Okay. Now, if we go back through the previous examples, okay, we're talking about small samples, so we have to know, okay, are both sample sizes at least 30, yes or no? Run through all of these flow charts, and basically in this example, we're going to get down to either one of these two. Okay, and that we have to make sure we understand that. That's the statistics that we have to understand before we input this information into our calculator. So it says the annual earnings of 15 people with a high school diploma and 12 people with a bachelor's degree or higher are shown. Okay? It says, can you conclude that there is a difference in the mean annual earnings based on the level of education? Use alpha to be 0.10. Assume populations are normally distributed and the population variances are not equal. Okay? So let's go ahead and write down our hypotheses. Okay, so we want the idea that it says, can you conclude that there is a difference in the mean annual earnings based on level of education? Okay, now it does not say the direction of difference, right? So let's just say here that mu bachelor's degree is not equal to mu of a high school diploma. Okay. So then up here, obviously, we would assume that they're the same. Because they ask us to conclude this, and this is a statement that we've seen multiple times. When they say, can you conclude, they are implying that that difference that they're asking that you can conclude about is the claim. Okay. Can we conclude that there is a difference between earnings here? Okay. Now, my hope is that you realize that the sample sizes are small and they are different sizes. Okay. So that alone, because they're different sizes, tells me that these are independent. Okay. They are not matched or paired. Now, we know that variances are not equal. Okay? Population variances are not equal. So we get up to this question here in the flow chart. Are the population variances equal? Answer to that is no. Okay? So in our situation, this is a non-pooled test. Okay? If we would have said yes, then we call it a pooled, or there's another word that they use for pooled. I have to look it up. Usually, probably 99% of the time, they're going to say pooled. So when we get to GeoGebra, okay, we have to decide what test. Okay, so we are going to do a t-test. Okay, because the sample sizes are small. Okay, and independent. We're going to do a t-test for difference of means. That's what we're talking about collectively. All right, so then you see here your null hypothesis is already established as 0. That's nice. That's what we want. Okay. The alternative hypothesis, we want them to be not equal. Okay. Pooled or not pooled. So if it was pooled, we'd check mark it, but it's not pooled, so we're going to leave it open. And now you can see that the rest of the input is very similar to what we see established in this summary of our data. We got to type in the mean, so 27,136. Okay. The standard deviation of that sample, 2318, and our sample size of 15. Then we're going to go to our bachelor's and type in 34,329, 49,62, and then size of 12. Once you type that all in, it will, I got to hit enter. It will calculate your information for you. Okay. Now, all we have to do is realize what was, and you can do this a couple different ways because they give you, actually, can we do this a couple different ways? They give me my test statistic, but they don't give me the critical value. So if I want to use the critical value technique, Okay, we have to use, I think we said alpha in the problem was 10%. So if alpha is 10%, we would have to run through and figure out what are the key values that create our rejection regions. Okay, so this would be 5% area there, 5% area there. And in order to do that, then we need to grab Excel and we'll type in equals. Okay, we'll go t.inv. Okay, now you got options here. You can do it one of two ways, because for whatever reason the t distribution gives you a two-tail command. You see where it says .2t there. If you want to use that, go ahead. If you do that, you're going to use the full alpha. So if I go .2t, okay, you're going to use the full alpha of 0.10. Okay. Now, degree of freedom, this is where it's kind of a pain in the butt. It's nice because if I use GeoGebra in tandem here, because of the fact that it was not pooled, I can use the degree of freedom that GeoGebra produces. That make sense? Okay. If I don't use it, I'm doing it all by hand, my degree of freedom has to be found using this tool here. Okay. Now, they go n-1 and n-2, the smaller of those. Okay. So the smaller of those, you might be thinking, okay, well, if we have 15, it'd be 15 minus 1, right? So our degree of freedom should be 14, right? Look at what GeoGebra did. Okay. GeoGebra gave 14.82 back. That's not 14, right? If you remember back to, so this is just the dynamics of using technology in place of the actual formulas. Back in chapter 9, when we did this with, I guess it was chapter 8. Find out where that discussion took place. Maybe it was chapter 9. All right, so this was section 8.5. There was a discussion about using what's called the Satterthwaite's approximation to find the degrees of freedom in a situation where you're using the key distribution for the difference of means. Now, this was what we were doing here was we were finding the confidence interval in 8.5. Okay, that right there is most likely what GeoGebra is using to find that degree of freedom. Okay, and what happens is that is ultimately a better approximation of degrees of freedom than what n-1 is. Does that make sense? Okay, so that is probably what they're using. Okay, if we had time, maybe I'll do this later and just show you tomorrow that worked out with our values. Maybe that does give that 1.84 number that they're reporting. Okay, 14.8 number. But if we take that value and type that into, so when I go 14.82, I think it was 12. That's going to give me my critical value. Okay. If we were to type in using the idea of what the notes discuss in regards to finding the smaller of the two samples and subtracting 1 from it. Okay. So I'm sorry, I apologize. I said 15 was the smaller. 12 is the smaller. Subtract 1 from that, and I get 11. Let's see what that two-tail critical value looks like when we use 11 as my degree of freedom. So 0.10 is the probability, and 11 is the degree of freedom. Do you see how they are very close to one another? Okay. But that 1.76 is probably a better value to use in as our rejection region than what this is. Okay. So 1.76 will be that rejection region. Let's go ahead and write on here. So negative 1.76 and positive 1.76. Those are my rejection regions. GeoGebra was telling me that the t-value that we are finding our test statistic is negative 4.6. So it is all the way over here, negative 4. So that tells us to reject the null hypothesis. Okay. There is sufficient evidence to support the claim that there is a difference in earnings. Okay. And if I think about this, so if I reject that, okay, then when I say UB minus UHS is not 0, okay, and if we were to look at these values, we can argue then that bachelors are going to make more, statistically speaking. We now know that bachelors collectively, if you have that degree, you're going to make more than high school. Okay. It's been years ago that I saw this article, so it's changed since then. It's probably, the gap has probably increased, and is what I would argue, that like having a high school diploma, like lifetime earnings is like just around $1 million. Okay. Bachelor's plus was like 2-point-something million. Okay, so quite a difference between the earnings of just having a high school diploma and then a bachelor's. Now, and I don't know, maybe that gap isn't widening, because like if I were going back and I was back in high school, I would look at, and I'd probably still go to college, but I'd look at some of these jobs like P&G, and I mean, there are some lucrative jobs out there, or like Husky or the refinery things, those other businesses out there that make some substantial amount of money without college degrees. Yes, Blaze. Yes. Uh-huh. No, so it puts a substantial list together, right, of data that gets spit back out, information gets spit back out, and several of them, like it gives you critical values for a one-tailed test and critical values for two-tailed tests. So basically what it's doing is setting up, because it doesn't know what your test is when you put things in. It doesn't know what your alternative hypothesis is. So it gives you the criteria to use regardless of your test. Does that make sense? It gives you your standard deviation, I think. It gives you your variance. It gives you your means. Those are things that we're really not needing to do the test. If we're doing it by hand, those were things that we found on the way to completing the test. But ultimately, when you look at that readout, And even here and this was the point of me going through the critical value strategy here. When we look at the readout, what's the most important value that they give me up there? That's the most important value, okay? Because if I want to look, this other stuff has its place. It's important to us, okay? But the reason the p-value is so vital and useful is that if I take the p-value and compare it to alpha, our p-value is 0.0003. Our alpha was 10%. What do I do when p-value is less than alpha? You reject. I get the same result, okay, that I reject the null hypothesis, and I didn't have to do all of this garbage here with finding the critical values and all that kind of stuff. Does that make sense? The data analysis stuff on Excel provides all of this information. It provides all of this information as well. Okay, the table structured a little bit differently, but it provides all this stuff. But somewhere in there, it will say p-value. That's the thing that we're ultimately probably is most useful to us. Does that make sense? All right. Why don't you guys take a minute and take this question. Well, you guys probably don't have GeoGebra, do you? Download GeoGebra, okay? Because here's what's going to happen. I'm going to give you a quiz later this week, okay? And in order to navigate that quiz in an efficient amount of time, you're going to want to use GeoGebra. You're going to want to have Excel as well, okay? So I want you to be able to utilize these tools, these resources, so you need to have them, okay? So take the next few minutes and download that. Yes? Yeah, the fifth one. The fifth one is the one that I use in class. So, and that's just my. If I were a student, I would want to be using what I see in class. Does that make sense? The obviously, I'm also the same mindset that I want the newest and best thing out. Right? That makes sense. So 6 is newer. It might be better. But there are things in 6. There's settings and those types of things that are in different locations than what you're going to see me use in this. And I've never worked with 6's probability. I don't know if it's any different than 5's. But the rest of the calculator, the graphing stuff, which we're kind of away from now, not going to be using to the end of the year, or through the end of the year, is substantially different in 6 than it is in 5. Excuse me?
Do we always use the estimates in terms of the, like, like the drop-down box right here? Do we always use that for the question? Do we use something different?
So this is, well, no, this one, because this one,
it's my T.
Right, we were doing a T, so the Z estimate is used when more than 30, and you know the population standard deviations.
We just use those two for like.
Yes. Yep.
Okay.
Yep. So right now, guys, when we look at our drop-down window, so this can help us even going back into chapter 9. If I'm on GeoGebra, okay. So the question was, well, which one of these do I choose? Which I understand could be a task in trying to decipher, because you've got 12 things here that 14 things actually that is going to, obviously you got 1 out of 14 chance if you don't know what you're doing to pick the right one, right? These up here are for one sample. Okay, you guys see this little gray line right there in the middle separating. These are for one sample. So Z-test for one mean, Z-test or t-test for one mean, and we know how we decipher between those two, right? Population standard deviation is known, and sample sizes are large. Population standard deviation is not known, sample sizes are small. These are then the, no, I guess it's not broke. I guess that gray bar is not breaking them up that way. Why? Okay, we're not doing estimates. Okay, we're doing tests, right? Okay, I guess I got to read those. So we're doing Z test, T test for those 6 things. Okay, so we were just doing the differences. What these are going to do, if I click on one of those, gives you your confidence interval. Does that make sense? Okay, and that's what our confidence intervals are, estimates, because we start with a point estimate, and then we add the standard error to both. We add the standard error, and we subtract the standard error from our point estimate, which is the mean, and that's how these two numbers are getting generated there. You can see that right here. Okay, so this one's a t-test for a mean, and this one's a t-test for the difference of means. It doesn't come out and say it in words, but it will tell you that you have 2 samples. So this is if we only have 1 sample. This is if we have 2 samples. And even if you do check the test for a mean, use that one, and you start typing your information in, and you type it in, you say, okay, well, I've got this other information in my problem, and I don't have anywhere to type it in, so that maybe leads you to default to this. Yes? Say again? Oh, you go up to View, and then down to where it says Probability Calculator. Does yours have it? There it is. Yep. Yep. So some of yours, so mine, the way I've set mine up to operate is that it creates a new, it just opens it in a completely new window, like this. Okay. You can, so a lot of yours initially when they open up, it opens up like this, yeah, on a side pane or panel or whatever you want to call it. If you close that one, it makes it bigger. If you want it to pop up as a singular window, now it won't do it because I don't have the other pane open. If I want it to jump out as a single window and 2 of these things are open, I click that button, and it'll pop out. And what I've done is once I've done that, I go up to Tools, I guess it's Options, and I save Settings, and then the next time I open it up, it will pop out as a separate window. Just a preference thing. Some people will say, well, I'm not getting what you got. Well, it's just organized differently. Is it okay with everybody? Why don't you run through, well, we've got that. Why don't you guys run through this last one? So the manufacturer claims that the mean calling range in feet of, should say its 2.4 gigahertz cordless telephone is greater than that of its leading competitor. He says you perform a study using 14 randomly selected phones from the manufacturer and 16 randomly selected phones from its competitor. The results are shown. Can you support the manufacturer's claim? Assume that populations are normally distributed and population variances are equal. Okay. So let's write our hypotheses, H0 and H1. Okay. Manufacturer claims that the mean calling range of its 2.4 gigahertz cordless telephones is greater than its competitor. So we're saying mu of the manufacturer is greater than mu of the competitor. Okay. The null hypothesis then would be that the manufacturer is the same as the competitor. Okay. Now, if you want to make this less than or equal to, that's fine. She'll make it equal to. But this was the manufacturer's claim that they had a greater range. Yes. Okay. So when it says variances are equal, okay, variances are equal, that is the not pooled, or sorry, that is pooled. They are equal, they are pooled. Okay, so we need to check that box. So once we have that, then we're looking for a t-test, difference of means. Null hypothesis is static. It's always going to be 0. You could change it, but there's no need to. It's always going to be 0 for us. It's going to be 1275, 45, 14, 1250, 30, 16. Check the box for pooled. Scroll down. I'm sorry, yes. So the alternative hypothesis, thank you. Because this is greater than, right? So we want greater than here. We want a right-tailed test. Thank you. So now I come down and I'm going to look at my p-value. Okay? Alpha was 5%. If the p-value compared to alpha, p-value is 0.04, alpha is 0.05. Okay? P-value is less than alpha. That means we reject the null hypothesis, right? So we reject that. And if we reject that, then we can say there is sufficient evidence to support the manufacturer's claim at 5%. Does that make sense? Okay. What if his claim was at 1%? We wouldn't reject then, right? Okay. And that's the idea, that rejection is based on our acceptance or our level of being okay with type 1 error, okay, which was rejecting a null hypothesis that should have been not rejected. But in this case, so that's why a lot of reports will just give you the p-value and let you decide what do you want alpha to be, okay. Does that kind of make sense? Is that much easier than running through all those formulas? Yeah, let the tool do that work for us in this situation. And that's kind of how the next several sections are going to go. I'm going to introduce, we'll do at least one problem by hand, okay? And then after we do it by hand, and the reason I do this is so that you gain an appreciation of what the calculator is doing for you. But we'll do it all by hand. And then everything after that, you can use Excel or GeoGebra. There is, have you guys seen, when you guys open up a question in your homework, and it has like the box that you can cut and paste, like it gives you the raw data. Does it ask you if you want to copy it to your clipboard or open in something called StatCrunch? Have you ever tried opening it in StatCrunch? Does it work? Okay. That's why StatCrunch is much like IBM's SPSS that I showed you the other day, but I think it's a little bit more user-friendly. for elementary statistics. But I didn't know if you guys had access to that. Okay, so maybe I'll introduce a little bit of that to you and show you how convenient that is. Okay, very similar to Excel and its structure. So over the next couple of days, we'll do that type of thing. I don't know how far we're going to get this week since Wednesday, 2-hour delay, Thursday, 2-hour delay, Friday, 2-hour delay. Okay.